I'd like to introduce you to Dr. Ekbal Hussein, who, having chatted with him, I discovered that he went to college, the place where I used to work for 26 years. So Dr. Hussein, he first of all went to Sheldon School in Birmingham. Grew up in Birmingham, went to Cadbury Sixth Form College, where he studied a number of subjects, maths, further maths, chemistry, physics, I believe, but not geology. And then on to Cambridge University to do natural sciences there, where he developed an interest in geology. And so, completing his degree there, he then went to Leeds to do a PhD in geophysics, and since then he's been employed at the BCGS at Keyworth, and the specialist topic is to do with natural hazards, and tonight he's talking about disasters by design. So I'm sure it's going to be a good talk.
Thank you very much. Thank you, and thank you all for having me and for a nice cup of tea. It's nice to talk with a cup of tea in my hand. Just before I start, just a heads up to everyone, for those who haven't been to the British Geological Survey in Keyworth, we have our open day on the 8th of June this year, and that's open to anyone and everyone to come along and see what we do. We are funded by yourselves, the taxpayers, because we're part of the government. So please come along. All our doors will be open and all the bells and whistles will be shown and all the toys will be out. They will have a ticket system. It's free, but we do have a ticket system because we only have a certain amount of capacity on site. So get in there early when they come out. The tickets aren't available yet, but I'll be there demonstrating earthquakes. Kids love it. Adults love it too most of the time. But yeah, come along. We'll have all the toys out for you to see. But today, I'm not talking about the toys. I'm talking about something that I'm particularly passionate about. And this is part of my research. Well, most of my research is going to space agencies and flying satellites. But I'm not going to talk about that today. I'm going to talk about why natural hazards turn into disasters. So why does an earthquake in any particular part of the world result in a disaster, and other parts of the world it does nothing? And the most important thing I'm going to talk about today is that I'm going to use earthquakes as an example to talk about the sort of components of a disaster or the recipe for a disaster, but this is relevant to every hazard. So you can use the same ideas for hurricanes, landslides, tornadoes, tsunamis, anything like that. But I'll use earthquakes because that's the one I know most. So first, what is an earthquake? And where are they? So an earthquake, we don't need to tell you, are a sudden release of strain energy in the ground along these big fractures that we call faults. And this is a map of the last 30 odd years of all the major earthquakes in North Africa, Africa, Middle East, Central Asia, and Europe. And every circle there is an earthquake. And the key patterns to point out here are the most obvious ones. And I think these are also the most important ones. In the oceans here, you see the earthquakes fall along the narrow, long lines. And we've known this pattern for many, many years, and since the 1960s, in fact. And that's exactly where the plate boundaries are. That's where plate tectonics were discovered, along the oceans. But if you look in the continents here, if I look, say, like Greece, there isn't a line. Almost all of Greece has had earthquakes. Same in Mongolia, same in Central Asia, same in Iran. There isn't a line. So the traditional model of plate tectonics doesn't work as well in the continents. And so what we say in the continents is that the earthquakes are distributed over large zones rather than lines that are defined plate boundaries. And in fact, the challenge here is that 75%, or 3/4 of all the most deadly earthquakes in the world have happened in this zone here, from Portugal all the way to eastern China, in this continental zone, where it's hard to define where the plate boundary is. And that's the danger. That's the broad challenge that we're working on for earthquakes. And the country I'm going to talk most about today is Turkey now. And because almost a year ago, so you will remember in the news, there was 2 devastating earthquakes And I'm going to use that earthquake as the case study to understand some of these issues. And Turkey sits right there, in the middle of that dangerous zone. So I'll zoom into Turkey in a minute. Here. And I love Turkey. I did my PhD studying Turkish tectonics. It's because of this. If you look at this Turkey, the GPS, each of these arrows here is a GPS station, a really highly sensitive one. And it shows this absolutely beautiful anti-clockwise rotation of an entirety of the Turkish landmass. And this rotation is happening because Arabia is a big solid beast. It's punching up north at about 15 millimeters per year, which doesn't sound like fast, but when an entire continent moves that much, it's quite a lot. That's a lot of energy being punched into Eurasia. But Eurasia is absolutely enormous, so it's not going anywhere. So a strong Arabia punches north into Eurasia, and the Anatolian plate here, this tiny little microplate, it gets squashed between two giant beasts. As well here, this is the Hellenic subduction zone, what sits underneath Greece basically. This is pulling the entire landmass of Anatolia. So Arabia is punching north and pushing, and the Hellenic subduction zone is pulling. What poor Turkey does, stuck in the middle, is move along these two giant structures. It's squeezed out like someone stamping on toothpaste. And the paste that gets squeezed out is Turkey. This is what's happening, Turkey. On these two big blue lines, there's faults. The north one called the North Anatolian Fault, and the east one called the East Anatolian Fault, named very imaginatively. And the entirety of Turkey is moving along those lines. So I did my PhD on the north one. I'm going to focus on that one for just a minute. Why? Because it's very interesting, and because it's had a series of very large earthquakes, very interesting ones. So in 1939, there was a very large earthquake here, magnitude 7.8. Until last year, the largest earthquake Turkey has experienced. In 1939. In 1942, a few years later, another earthquake there, large earthquake. In 43, another large earthquake there. In 44, 57, 67, 99, and 2022. So, which way do you think the earthquakes are going? Where do you think the next one's going to happen? Right? It doesn't take a genius to see that pattern. The earthquakes started in the west and have been migrating to the east, like a zip. You're undoing a zip. All the energy is being released like a zip. And why is it dangerous? Until early last year, we thought the dangerous area was here, Istanbul, a city now of 15 million people. The last time Istanbul got hit by an earthquake was 500 years ago, where its population was 150,000. Now it's 15 million, and that's where we thought was the main disaster waiting to happen. And it still is our biggest concern now. But however, early last year, that's where those two earthquakes happened, on the East Anatolian Fault. An area that we knew was dangerous, but wasn't high on our list of potential disaster zones. But that's where it happened. And what happened in that earthquake? Shaking lasted over a minute. So a minute doesn't sound like a lot, right? It doesn't sound like long. But it's long enough to deal a gigantic shock to the system. And in some parts of the country, the shaking exceeded 1 g gravity. So what does that mean? To exceed 1 g means that everything you can throw things into the air. So if I throw a ball into the air, the vertical acceleration has to exceed gravity, right? So when the Earth shakes and throws things into the air, it literally throws things into the air. Entire buildings get chucked into the air, right? Imagine a 50-story building getting chucked into the air. That's what 1 g does. But luckily, not many places exceeded that. So most places just shook very hard. Don't worry about that. And aftershocks are still happening. Almost a year later, aftershocks. The level of aftershocks in Turkey is still higher than background levels. So it takes many, many, many months for the aftershocks to die back down to background levels. And these are very big earthquakes. So if I were to take that there were two earthquakes, one at 4 o'clock in the morning and one 9 hours later. If I would just take the first one, the largest earthquake, it ruptured a fault plane around 300 kilometers long. So if I were to take the map of that shaking and just translate it onto the UK, it looks like this. Imagine a fault line from the Humber estuary all the way down to the Bristol Channel. And imagine the entirety of the UK being split in a line along that by about at least 4 meters. That's that first earthquake. If I were to add the second one on 9 hours later and join them together, it'd be like an earthquake from London to Carlisle, from London to Edinburgh, to the Scottish border. Imagine the entirety of the UK being split by half, by 4 meters. That's the length of fault line that moved. So these are very big things. Turkey just is a big country, so in comparison, it looks small when they put on the map. And this, what did we do? So I work with satellite data especially, to understand where things have changed, where things have moved immediately after the earthquake. And this is what we did. We drew a map of where things had moved within a couple of days of the earthquake. And red shows where the ground has moved to the top right, and blue shows where the ground has moved to the bottom left. And you can see this fault line popping out here very nicely here, with the red and blue sort of transition across each other. That's the fault line. That's where it moved. And so if I were to stand on the bottom here and start walking up and see how much the ground had moved to either side, you'll see here that's the blue line. And the red line is the same for the second earthquake. That's up there. You can see most of the ground moved at around 4 meters for the first earthquake, going up to about 7. In the second earthquake, this top one, it moved around 7 meters. That's almost the length of this room. Imagine the entirety of the UK being split by that much. That's how much ground moved. And these are some photos of the post-earthquake reconnaissance. So this is the fault line here that moved. It's all rubble now, and luckily it missed the house. It just went to the left of that house. But it went to their garden. And this is the fence. If you see that fence here, it was offside by about 6 meters. And this is another example of a farmer and his olive tree farm. And this tree here got snapped in half. That's the other half of the tree right there. And this is where this other half of the tree is here. And both halves are still alive, amazingly. So they're thinking of turning into some sort of memorial. This is what one half of the tree looks like. So that's an amazing sort of thing. It ripped the tree in half. So if I were to stand on this side of the fence, of that wall here, and look across to the other side where the wall has gone, you see that it's moved to the left. Right? If I stand this side, the wall's over there now. That's what we call left lateral motion. If I were to do the same from the other side and look over this way, you see it will still be the same. That's what we call left lateral. And that's what the majority motion on this fault is. However, if I were to stand on this side of the tree and look across, you'll see it's actually moved to the right. So a fault can't do both. And this is why it's always careful to it's always good to be careful when you look at the news about these things. So this was movement in the earthquake, but this is actually a landslide. Because the fault moved that way, not that way. And the only way you can go that way if something else makes it go that way. So this is a landslide. So it's actually, it may look like an earthquake that's gone through here, but it's not, it's a landslide. So what do? We take all this satellite data and take GPS measurements, seismic measurements of the ground shaking, and then we can build these sophisticated models. Say, this is the fault line, but the fault line goes down to around 15, 20 kilometers. So what we can say is, okay, where in the ground has it done all the movement on the fault plane? And we can build models like this. And this is the first earthquake. It goes off, it's about 300 kilometers long, and the red shows where it's moved the most. And at the top of that line is where the ground is. And you can see that most of the movement actually happened at around 10 kilometers underneath your feet. Around 10 meters of ground moved down there. By the time we got to the surface, it was around 4 meters. That's what we saw in the satellite image. So most motion happens beneath you. What's interesting about this one is that if you go along west from that way down here, most of that fault is moved in red, but there's a little gap there, right there. This is where nothing moved. That's where basically the fault ended. The earthquake shaking ended. And that's where the energy did not get released. And that's where we think the next earthquake will happen. Because this one didn't release all the energy in that gap there. That's what we call seismic gaps. So stepping back out now to look at Turkey. So this is the seismic hazard map for Turkey. And this was done in 2018. And these are maps that most governments in the world now can make. and we can make them certainly at the BGS. And what they do is take the history of all the earthquakes in the country that we can measure, combine that with all the satellite measurements and all the GPS measurements that we make now these days, and then build a map of where we think the energy is getting stored on all these faults. Because where you store energy, you eventually have to release it. And the most common way of releasing all this energy is through an earthquake, right? So this map was made in 2018, before we knew about these earthquakes. And all the red line bits here are where we say it's high hazard. So the obvious place, the North Anatolian Fault, the East Anatolian Fault, all these places in the western Turkey. So we knew exactly where it was dangerous in Turkey. We've known for many years where it's dangerous in Turkey. And we were sort of vindicating almost. So these blue lines here is where the 2 earthquakes happened in February last year. And it's exactly where it's red. It's exactly where we knew the hazard was high. So I have a question now. So if we knew the hazard was very high here, that this place has a very high earthquake potential, and that there's a high amount of shaking expected from earthquakes on here, why did it result in the disaster that we experienced, that we saw in the news? And that's the main question I'm trying to answer. I'm going to try and answer today. Because the answer is actually a bit more complicated. And this is the disaster that unfolded. I'm not going to show you too many pictures of the disaster because we don't need to show you these things. But what happened? 59,000 people died. In that 1 minute of shaking, 59,000 people died. The deadliest earthquake in the last decade at least. 51,000 of these in Turkey, 8,000 in Syria. I will come back to that Syria thing in a minute. The population of some of these cities, Kahramanmaraş, Hatay and Adıyaman, they were decreased by nearly a half. So these are cities near the epicentral region. Nearly 250,000 buildings were damaged. Damaged in the sense that they either collapsed or they were so badly damaged they're going to have to be destroyed anyway. And 11,000 in northern Syria, at least. This is from the early reports from within a few weeks of the earthquake. And there's an estimated at least $45 billion of direct damage. This doesn't count the reconstruction costs of people and their livelihoods and mental health and all that. This is just the direct damage to the buildings. $45 billion. So by no means the costliest disaster, but it's still a very expensive bill to foot for any country in any place. So that's what the impact was. So we knew the hazard, and yet this happened. And that's what I really want to start talking about now. So let's start with the basics. We're stepping back out now, outside Turkey, to look at more general patterns. This is a map of earthquake size on the bottom, magnitude, versus the fatalities, the impact it's had on the left. And let's make the first assumption that big earthquakes kill more people. Big earthquakes produce more fatalities. And that's quite an obvious assumption to make. And if you look at this graph, this is a broad, obvious trend in that direction, where big ones kill more people, right? But it's not as simple as that. And I'm going to show you some examples to demonstrate this. This was the Turkey earthquake last year, magnitude 7.8, killed around 60,000 people, more or less on this trend. This was the largest earthquake we've ever measured in 1960 in Chile, a magnitude 9.5 earthquake, killed around 3,000 people. So 3,000 is a lot of people still, right? That's a lot of people to die in any event. But this scale here is what we call a logarithmic scale. It means that any one step here isn't just 1 degree increase in energy, it's 32 times increase in energy. So a 7 is 64 times stronger than a 5. And I can't do the sum for the next one, but in my head. But a 9.5 is many, many times bigger than a 7.8. Many, many, many times bigger. And yet you only killed 3,000 people. I say only, that's still a lot of people, but compared to 60, it's a lot. It's not a lot. This is Haiti, probably the deadliest earthquake this century. A 7.1 earthquake in 2010, many will remember that in the news, killed anything between 100,000 to 300,000 people, depending on which report we read. There's lots of debate around that. We can talk about the politics later. But it killed a lot of people. It was a very, very dangerous and deadly earthquake, a 7.1 in Haiti. A year later, in 2011, the same size earthquake in Pakistan killed 3 people. Exact same size. In fact, it's an awful thing to say, but it killed 5 people. But the shaking induced 2 women to give birth early. So the net was 3. So this is a strange way these statistics are counted, but it's the net deaths. But yeah, 3 people. Same size earthquake in 2 places killed 300,000. In Pakistan kills 3. So there's more to this story than just the size. And this is the answer. So I'm going to tell you the answer to it all, and then I'll start from the end. This is why a natural hazard becomes a disaster. Because of 4 things: the exposure, the poverty, corruption, and ignorance. And because I couldn't resist the temptation, I've called these the 4 horsemen of disaster risk. And for the rest of this talk, I'll just go over each one of these in some detail, not a lot of detail. So what do I mean by exposure? How am I doing for time? I'm okay for time. It means, quite simply for earthquakes, where do people live and what kind of buildings do they live in? So the first part of that question is actually very easy. We know very well where people live because we have census surveys. Every 5-10 years in most countries in the world, there's a survey done of where people live and what kind of population centers are they living in. And and we can supplement that with satellites. Most of the world is being spied on by us, the US, or many other combination of other countries. And even not spying on them, we're looking at other things to look at population dynamics. And this is a map of the global population distribution. And the most obvious observations are often the most useful ones. Most of the world is empty. Believe it or not, most of the world is empty. But there are places that have extremely high concentrations of people, particularly this band from Europe through the Middle East, South Asia to East Asia. There's an enormously highly dense band of dense population in that region. And that matters, because that matters for exposure. The second half of this question is actually harder. The second part of the question of what kind of buildings people live in is hard. Because to do that, we'd have to go inside every single building in the world with an engineer to test the walls and the buildings and the columns. We cannot do that. It's completely impossible to do that. And notwithstanding the expense, but we don't have that many engineers. So we have to come up with other ways. So we make lots of assumptions. In fact, that's the frontier of science at the moment. How do we make those assumptions in a better way to better represent the building stock of a country or a city or any sort of neighborhood? And that's where a lot of my colleagues are working. So I don't have a nice figure to show that because we don't know the answer to that one. But we're working on it. But why does it matter? Why does that population distribution matter? This is the number of fatalities in the last 1,000 years in earthquakes. The bigger square, the more people have died. And the yellow lines here are what we call the subduction zone in the world, where one plate is being pushed underneath another. And that's where you get the biggest earthquakes, the really, really, really big tsunami-genic earthquakes often. You'll see the Japan, the Chile earthquake, these are the really big earthquakes, the 2004 Boxing Day tsunami earthquake. That's what happens here along these yellow lines. They're enormous earthquakes. But this is where most people die, away from the subduction zones, where you get the big earthquakes. So that's where most people die, away from the large earthquakes. And clearly, 85% of all the world's fatal earthquakes happen in the red circle there. The majority of all the world's fatal earthquakes happen there, away from where you get the big earthquakes. So what we say is that some countries have a higher exposure to earthquakes compared to other countries. And location clearly matters. Where you live matters when it comes to your exposure to earthquake risk. So that's horseman number 1. Horseman number 2, poverty. This is my favorite slide. I wish everyone knew this slide because it's actually an amazingly good story. And I'll tell you why. So the first half isn't, but this is the world's population growth since 1820. In 1820, the world's population was about 1 billion. Now it's 8 billion. And this graph, a lot of people knew. Everyone knows this graph, the growth of the world's population. But I'm going to look at the number of people in the world who were extremely poor. That's this red line. What do I mean by extremely poor? This is a very well-defined categorization. It's if you earn less than $2.1 a day. That's the hard limit to be extremely poor in the world today. And what does that mean? It means you cannot feed yourself on a daily basis. You can't get food every day. That's what extreme poor means in the world today. So, in the world, in 1800, there was nearly 1 billion people in extreme poverty. And that number went up with global population growth, but something happened in the late 1960s, 70s, 80s. The world's number of people living in extreme poverty decreased, even though the world's populations kept going up. If we were to turn that into a percentage, it looks like this. That's a percentage. So in 1820, nearly 80% of the entire world could not feed themselves on a daily basis. And an amazing thing is, this is development in progress. The world number of people living in extreme poverty has been going down as a percentage for since the last 200 years almost, down to around 9% of the 8% of the world today. And that's an amazing story. That's great. And long may that trend continue down to 0. That's what we want. It's so many people come out of poverty. All the world's media could have ran this headline. 137,000 people escaped from extreme poverty since yesterday. All the world's media could have ran that headline every single day for the last 25 years. That's how many people come out of poverty every day. And that's amazing, right? That's good. So why is it one of my horsemen? It's because of this. Poor people lived in buildings like this, made with local materials, with wood, bamboo, mud, whatever they've got lying around. They made their homes with what they had around them, not brick concrete. So this stuff can absorb energy, because wood can sway and bend, and bamboo can bend and absorb energy. And even if you collapsed, the straw falling on you wouldn't kill you, usually. That's what extreme poverty looked like for buildings. This is what people are doing now. This is a photo I took in Bangladesh. This family is coming out of this bamboo mud tin house in the background, and they're building their own homes. And this is the challenge. 96% of all the world's poor people, extremely poor people, built their own homes. They didn't have degrees in engineering, they didn't have degrees in architecture, they didn't have degrees in design, they didn't have degrees in masonry. They built it themselves, or with the help of the neighbor who went to see someone else building, mixing cement together. That's as good as it gets in terms of training. Why? It's because these people are still poor. They're coming out of extreme poverty to just poverty, whereas we're up here. They made a critical jump coming out, but they're still extremely poor. We cannot forget that. And what do? They get their bricks like this, and they pile up the side on like that. Why? Because it takes fewer bricks to build a wall. If you go outside and look at the brick wall, probably this one, you see the bricks are flat, like that. And so you have a bit more surface area of the ground, and that matters for that strength of the wall. But it takes more bricks to build your wall, and therefore it costs more. So these people are still poor, and still they do things like this to save money. Here's another example. This family is coming out to that tin home on the left, and moving into this concrete brick home. And you can see the same ideas. The bricks are side on, pillars are very thin. The most of the strength of a building's strength is in the pillar. And you want at least 3 or 4 rebar rods within that pillar. At least. These have 1, if not 1, 2. Because rods are expensive. Rebar is expensive. And yet this house looks fine. They can live in it. But when the ground starts shaking, I'd rather be in the one on the left than the one on the right. So what do we say? We say that the jump from extreme poverty to just poor, which is still very poor by any one of our lived experiences, often increases the risk to earthquake shaking. So we want people to come out of extreme poverty, accelerate to poverty, and go to middle income as fast as they can. Because that's that dangerous zone in the middle there. Where have I gone? And why does it matter? It matters because earthquakes don't kill people, buildings do. This is a rather famous phrase by Nicholas Ambrasis. That's the danger. So that was the poverty when it comes to building style. There's another insidious form of poverty that is equally important, and I'll explain that with the Turkey example. What do we mean by poverty? So this is a map of average disposable income, i.e. how much money you've got left at the end of the month to spend on nice things like food and nice meals out. As you can see, southeast Turkey is where people are poorer. Most poor people live in southeast Turkey, and this blue line is where the earthquake happened. The poorer people in southeast Turkey. In fact, over 1.5 million people live below the national poverty line in the 10 most affected districts where the earthquake hit the most. That's a lot of people. Where am I? This is a map of total fertility, i.e., so this is quite an interesting stat. I've got a whole talk about this. Is how many children does a mother and a father choose to have? Well, most is about mother. Most countries in Europe at the moment, it's like less than 1.2 child per mother. And in this part of most of Turkey, it's around 1.2 as well. But in this part of Turkey, it's quite high. It's up to 2, 3, 4. Each mother chooses to have bigger families. Why is that important? It's because the number of children a mother chooses to have is directly correlated to the level of poverty within that family. It doesn't matter about religion, where you are in the world, doesn't matter if you're European, from North Africa, South Africa, East Asia. That has no impact on the number of children a woman chooses to have. It's only about poverty. And that in itself is an amazing statement. I have an whole lecture just on that statement, which I don't have time to go through in detail now. It's all about poverty. So large families are associated with more poverty. And that's where most families are, in southeast Turkey, where the earthquake hit. Another way of looking at poverty is looking at school sizes, classroom sizes. Again, more complicated story, but same idea. Southeast Turkey is where they have the large classroom sizes, i.e. another form of impoverishment. So, all that's saying is that social vulnerability is more acute in southeast Turkey compared to the rest of Turkey. And why does that matter? It matters, on top of all that, 6.5 million refugees, because of all the crisis happening in Syria for the last decade. Lots of really poor people coming out of northern Syria into southeast Turkey. And that's where they're all congregated down there. A lot of them are congregated down there. Poor people generally don't own the homes they live in or the land they're living on because they simply can't afford them. And more often than not, they're living in their homes illegally and badly built. And often in overcrowded conditions. So what we say is that all these matters make people more vulnerable. When those buildings start shaking, those are the places where you start worrying, because they're completely vulnerable. So that's poverty. Corruption. Let's define it to begin with. This is again another very complex topic, but it means the misuse of entrusted power for private gain. I ask you to do something for me, I'll pay for your service, and you don't do it. You abuse that trust. That's what corruption means. And you don't need me to tell you that corruption is deadly. In all its forms, is deadly, but particularly when it comes to this. And so how does corruption work when it comes to earthquakes? It matters because buildings. Remember, buildings kill people. Earthquakes don't kill people, buildings do. And the types and quality of your building matter. So how does a corruption work in the building industry? So this is the golden ratio. I mean, there are many of these, so this is a very simple depiction of how do you make strong cement. You make strong cement by getting 1 bag cement, mixing it with 3 bags sand with some mortar, and that gives you a good, solid, strong cement. You build your house with that, and it looks going to be a strong house. But cement is more expensive than sand. So if I happen to be a corrupt contractor, what do? I do this. I mix 1 bag cement with 6 bags sand, and the thing looks the same, feels the same. At the end, it doesn't behave the same. It's not strong cement. So when the earthquake happens, it shakes and it does that, because your building's not strong. Another form of corruption is putting buildings together in substandard ways, i.e. the brick side-on. That could be a corruption thing as well as a poverty thing. The number of rebar rods in a pillar. Remember I said you should have at least 4. But once the building's finished and cement's all done, you can't see what's inside the pillar. So the contractor could put 1 or 2 down and pocket the money for the other 2. And no one can know that any other way. No one can check because it's inside the cement. Putting buildings in the wrong places. This is quite common all over the world. It's not just a Turkey problem. You see about the UK, right, with buildings and floodplains and all that. There's a whole issue around there. But putting buildings in places where they're very much at risk, i.e. close to a cliff, where if the earthquake doesn't get you, the landslide will, kind of thing. And there are many examples of that. I'm not going to show you photos. There are many examples of that. And this is what corruption looks like. So after the earthquake last February, the UK sent a team out, and it usually does after major disasters, to do a post-earthquake reconnaissance survey. After the humanitarian crisis is over, we send people out, engineers, to check what happened. And part of what they do is take drill cores out of the pillars of big buildings, so rock cores almost. And this is what they found in some of the cores. They pulled out of these are cores from pillars of big buildings. And all the grey stuff is cement, and all the big balls there are pebbles. Very big pebbles, 6 centimeters, that one. That's about that big, right? So we often put aggregate in the cement to make it strong. But what they've done here, those geologists will know, you get rounded pebbles in the rivers, because that's the water. So what they had done was they'd gone to the local river, chucked out loads of pebbles, dropped it into the column to bulk out the cement. Because remember, cement's expensive. The pebbles are free. And no one knows any different because it looks the same at the end. But that is not a strong column. That's corruption right there. Another form of corruption is this. These are rebar rods that came out of the pillars. And they look pretty big and chunky, and they do. But the engineering code says you have to use ribbed rebar. Ridges, one with ridges on them. If you go outside next time you go to a building site, you'll see rebar rods have ridges on them. And that's because the ridges increase the surface area with the cement, and therefore you get a strong connection from rod to cement. And that makes that pillar strong. But ridged rebar is more expensive than smooth rebar. But when it's in the pillar, no one sees. But this is very clearly corruption, because the Turkish building code says you cannot use those. And Turkey knows how to do this. After the mega earthquake in 1999, Turkey updated its building code, its building standards, and gave very clear instructions on how buildings should be built. So Turkey knows exactly what to do. And he knows exactly what to do because that's the engineering department of the local university. So they know how to build buildings very well, even in big dangerous zones like this. But knowing the rules and enforcing them is a challenge. And that's a challenge in every country in the world, but particularly in this part of Turkey. And this is an example of corruption. This building block here, this block of flats, was on sale 2 years ago. And it says down here, look, in Turkish, I'll translate for you, it says, completed in compliance with latest earthquake regulations. And what happened to this building? It fell over. It collapsed. In fact, it didn't fall over, it completely pancaked. That's worse. And the builders who built this are now in exile. They've escaped Turkey because the government's looking for them. And they're not going back to Turkey anytime soon because they know what they did was wrong. And everyone who lived in that building, well, I'm not sure about that, but they suffered the consequence of their poor building practice. On the other side, we know good building practice works. This city, Erzin, sits right in the middle of the earthquake zone. I'll show you where it is. So this is the hazard map. Erzin sits right there, very close, very, very close to the fault. So where it got shook really hard, and nothing happened here. No injuries, just some minor damage to some of the buildings, but certainly no injuries. And how did this city survive? It survived because it's got a good mayor that actually went and inspected all the buildings as they were being built. And if anything was built badly, it was the mayor made the builders knock it down and build it again. This is what good governance does. If you build your homes properly, you can live in an earthquake zone and survive it. You don't need to live in fear of an earthquake in these areas. But, and that's actually a great story. However, Turkey has a major problem when it comes to corruption, particularly in this process called imar barişi. And this is a political tool. What it is that every election cycle in Turkey, the government will say, okay, we know you guys have built your homes illegally, using illegal practices, not following the code. But if you pay us a fine, we'll give you a legal license certificate. And it's a political tool to get votes. So in the last election, in 2021, last cycle of these, over 300,000 buildings in this part of Turkey that were most affected by the shaking were legalized using this system. So these buildings are not any better, they're not any different, they just now have a certificate that says we're now a completely legal building. And that's what I call legalized corruption. And this is completely legal in Turkey. And this is a travesty. So stepping out, how do we measure corruption globally? It's a very difficult thing to measure. You can't just get a standard, right? So the populations, it's a hard thing to measure. However, these guys, Transparency International, try to do this. They've been doing this since the 1990s. Every year, they do various surveys and lots of complex statistics to give every country in the world a score between 0 and 100. And 0 in this scale is complete and utter corruption. 0 is the devil, 100 is angel, absolutely no corruption. Sadly, no country scores 100, and thankfully no country scores 0. In case you're interested, the best countries in the world, the least corrupt, are also probably the most unsurprising, are the Scandinavian countries. Finland, Denmark, Norway, Sweden, New Zealand, they score very low on corruption. The most corrupt countries in the world, also probably not surprising, countries like Syria, Afghanistan, Somalia, countries like that. What's the challenge here? These are the most fatal earthquakes in the last 23 years. They all happen in orange or red countries. And if I were to draw a line in the middle, between 0 and 150, right? 50 is the middle. You're not corrupt or angelic, you're in the middle somewhere. 2/3 of all countries in the world score below 50. i.e. they are more corrupt than not, according to this score. So most countries in the world are more corrupt than not. And so if I were to put this another way of looking at this, so look at the wealth of a country, the income of a country, versus its corruption score. Remember, 100 is angel, 0 is devil. And you can see there's this interesting positive trend between wealthy nations being least corrupt. So if I were to draw this trend line, the dotted line, if you fall on, what it means is that if you fall on the line, you're just as corrupt as we expected you to be, given how much money you earn as a country. Right? So if you fall below if you fall above the line, you're less corrupt than we expect you to be, given your income. If you fall below the line, you're more corrupt than we expect you to be. So the less corrupt ones are, no surprise, Chile, Japan, New Zealand. The more corrupt ones are Mexico, Russia, Greece, also probably not a surprise. And this bit here is where it all goes to pots. So those are the good guys, less corrupt than we expect them to be. Where are we? Those are the bad guys. They're more corrupt than we expect them to be. And this is where it all goes wrong. These guys are corrupt, ignorance, corruption, these all messed apart and meshed together, and it's hard to disentangle all that. So this is where I spend a lot of time worrying. And why does this matter? It matters because 83% of all deaths in the last 30 years happened in low income, poor, and anomalously corrupt countries, i.e. in the yellow and the red bits. That's where most deaths happen. So that's Horseman 3. Horseman 4, bad design. This is a photo I took in Bhutan in the Himalayas a few years ago. And by every measure, this is a really well-built home. These enormous pillars, these are huge pillars, with lots of rebar rods. The bricks are flat. All the things I talk about, they did really well. But I'm going to draw your eye to this section here, right there. And I'll zoom in to show you what I mean. The reason we have big pillars and put bricks in between them and the plaster over the top is so the bricks are in between the pillars. In this one, on this wall, for some reason, the bricks are on the outside of the pillars. So there's nothing holding them really in. And so when the building starts shaking like this, actually it does that, and the building will probably survive. The building probably won't fall over, but what's going to happen to all those bricks on the outside of the wall? They're going to start coming down. One of the main reasons we say, if you're in an earthquake, don't run outside, because that's what's going to happen. If it's not bricks, it's glass, or power cables and that kind of stuff. It's always safer, almost always safer to stay inside and be under a table because of things falling down on you. That's actually what actually hurts a lot of people. That's where most injuries come from anyway. So what is this? This is horseman number 4, ignorance. They just probably didn't know that they shouldn't do that. And that's a really hard one to test, to check on. And why does this matter? It's because in Turkey especially, in the last, 10, 15 years or so, there's been an enormous decline in the number of students in Turkey coming out with geological engineering degrees, and a decline in number of people doing geophysical engineering degrees. And why does that matter? These guys know what they're doing when it comes to earthquake engineering, building homes. And worryingly, there are less and less of them. In Turkey especially. Despite the fact the number of engineering departments are quite high, in fact they're going up. The number of departments are there, the number of the students they're producing are there. And that's worrying because that's a group of people who know what they're doing when it comes to building your home safely to withstand earthquake shaking. And that's a trend that's the same in the US, same in the UK, same in most countries. The number of people who know how to build your home safely is decreasing in most of these countries. And that's a worrying concern. So that's where the ignorance thing comes in. So the homes still need to be built. So those are my 4 horsemen. Right? So I'm going to move on slightly to the next part of the talk, which is moving beyond earthquakes. Because the world, sadly, isn't just about earthquakes or floods or hurricanes or tsunamis or landslides. It's a complex jumble of them all. And this is what I mean when I say domino hazards. So let's think of an example. An earthquake, the shaking may trigger a tsunami, which we all know of. It also may trigger landslides. The landslides can block a river, and the river may flood a few weeks later. And that's what we call a simple domino hazard cascade. That's a very simple one, and we've seen this one happen in real life. This is what happened in 2011 in Japan. The Tohoku earthquake, a very large magnitude 9 earthquake, generated a tsunami. We saw those in the videos and the films. The earthquake shaking also destroyed a hillside, which is with the landslide, and that landslide destroyed a dam, which caused lots of flooding. In this particular earthquake, you'll remember, it also led to a man-made disaster, an explosion at a nuclear power plant. This is a very interesting topic to me, where natural hazard cascades connect to human disasters. That's a very complex field now. That's only we're exploring right now. So this is what we call a hazard cascade. And the exact cascade, not the exact one, a similar cascade happened in Turkey this year. And I'm going to go through this cascade with you. So let's go from the top down to the bottom. So top is where the earthquake happened. And I'll talk you through some of the hazard cascade in hours, weeks, and months following the earthquake. And I'll talk you through a couple of types of natural hazards, the geological ones and hydrometeorological ones, i.e. weather-related ones. So let's start at the beginning. Magnitude 7.8 earthquake at 4 o'clock in the morning. That's going to be important. At 4:17 in the morning, a very large earthquake shook. 9 hours. Oh, I forgot about that. 9 hours later, that earthquake generated a tsunami, a small one, admittedly about this high, but that's still a tsunami, and they are still dangerous. Because you can't outrun a tsunami. No matter if it's this big or that big, you can't outrun it because they come too fast. 9 hours later, there was the second big earthquake, a magnitude 7.6. This was at lunchtime the next day. Both earthquakes generated lots of aftershocks that are still outgoing today, large numbers of aftershocks. Both earthquakes generated liquefaction. It's when the ground becomes quicksand, things start sinking into it. That's another dangerous form of hazard that we still don't understand very well yet. Both earthquakes generated lots of landslides, thousands of landslides, some of them deadly. And remember, so at 4:17 in the morning was that first earthquake. What are most people doing at 4 o'clock in the morning? They're asleep, right? So imagine this. You're asleep, the whole world starts shaking. It stops shaking after about a minute and a half, and you do what you're meant to do. You're hiding on the table, hopefully, and then you run outside. Right? You're wearing whatever you were wearing in bed, because it's not safe to carry anything. You just run. What do you run out to? You run out to this, a winter storm with heavy snow, about a meter high, strong winds, biting chilly winds, and minus 19 degrees Celsius. That's what people ran outside to after that earthquake at 4:17 in the morning. And then that snow started to melt, caused more landslides. The earthquake, the first one, caused flooding because of all the shaking and the reservoirs and things started collapsing. The tsunami obviously caused flooding on the coastal zones. Where am I going? That's a link we haven't found yet. So the landslides causing flooding, we know it happens in other places. It hasn't happened in Turkey yet. The snow started melting, caused even more flooding. That's all within hours of the earthquake. This is a hazard cascade within just hours to days of that earthquake. A week later, there was another storm. By this point, most people are living in tents outside. You're living in tents and it storms. A torrential storm that led to more flooding, where 20 people died because their tents got swept out on the flood. A week after that, there was another storm that had these: a flash flood, heavy hail, and a tornado. And when I say hail, I mean yay big hail. Not the tiny ones we get here, big ones. And I'll show you a picture of what I mean. And then this is now, few weeks after, months after, people now aren't living in tents, they're living in container ships. Because that's how the sort of relief effort works. You go from tents to container ships and eventually you're home. Container ships are metal. And metal is bad because that's what happened about 2 months later. 40 plus degrees Celsius. So that's the hazard cascade that people had to endure and are still enduring to this day in southeast Turkey. And what was the consequence of that? The impacts were these: collapsed building, disabilities, temporary home issues, fatalities, homelessness, aid distributions, regional geopolitical tensions because of its Turkey, Syria, they don't like each other, political instability, food crisis, 4 million kids out of school, and who's going to pay $45 billion to build everything back up? That's the impacts of the hazard cascade. And that's what we're trying to deal with now. And we will deal with it because that's how we do. We pick ourselves back up. It just takes time. And these poor people have to suffer until we can get the aid and the reconstruction process ongoing. And the challenge here is that in red are the things that are affected by climate change. So this is one cascade that's happened this year. If this cascade were to happen in 30 years' time, all the ones in red would be worse. The impacts from all the ones in red would be worse. So climate change, so my thesis is that you cannot take geological hazard cascades and climate cascades and keep them separate. They have to be thought of as one. In 30 years' time, every single thing on this board will be worse, apart from the earthquake. So we can't ignore climate change here. And this is some examples. So this is a landslide that happened in an earthquake. It's blocked the river here. And see in the distance, Dejimenchik, that's a town. And that's the river about to flood, overtop that landslide. And it would flood that town in a matter of weeks. In this case, they've built a little drainage here where they'll slowly drain that lake. But if they hadn't, that's exactly what I mean by landslides blocking river and then flooding a town. Because that will overtop. And when it overtops, it cascades out into an enormous flood. This is the flood I told you about that killed 20 people because it swept away the tents. That's the kind of disaster that people have to deal with. And this is a sad story. This is in northern Syria. The earthquake destroyed a dam that was holding back a reservoir. And that reservoir just washed into and washed away an entire village. Really sad. And this is the hailstorm I told you about. It looks like snow. It's not. These are all hailstones piled up that look to look like snow. This was awful disaster. So thinking about what we do, what I do in my work, when it's trying to think about how to understand these cascades and the vulnerability people have, I like to use a simple model. Think of a city on the coast, like many cities in the world, Jakarta, London, Lisbon, all these big cities on the coast next to a hill, and it has this experience. So what happens? An earthquake happens, and the buildings shake. You get under the table, and the shaking stops, you run outside. And what should you do? The shaking lasts more than a minute, and you're on the coast. You run uphill because that's coming. Tsunami. This is my very, very basic clip art. Someone in my department will make this into a nice video at some point. This was me, though, and I'm not an artist. So you run outside, and you run uphill as fast as you can, because in 15 minutes, that tsunami is coming. On average, you have 15 minutes. So you don't have time to get your things. You don't have time to get into your car. You just run with your family and your children. I said family and children. What about that person? In 2020, there was an earthquake in western Turkey, in Izmir. A small earthquake, but generated a 1-meter tsunami. Everyone survived the earthquake. One person died in the tsunami. And that one person was in a wheelchair, because she couldn't get away fast enough. Remember, you can never outrun a tsunami, no matter how big it is. What about these people? Pregnant women, elderly people, people with families and children. This is where vulnerability lies. So, and then the person is on a hill. It's on a hill and you get a landslide a week later. So what do we say? We say that the changes in exposure and vulnerability during a multi-hazard cascade evolves over time. And that means the risk evolves over time too. So you can't think of your risk as that. As the whole system's evolving, your risk is evolving too, because your vulnerabilities and exposure is evolving with time. If you're in a wheelchair and you survive the earthquake, you are at a much higher risk to the tsunami than an able-bodied person. So we can't ignore the variabilities of risk and vulnerability. So how do we try and model all this? This is what we used to do. We used to get a hazard, an earthquake, find out who was exposed to it, i.e., this building, that building, these people, and find out how vulnerable they are, i.e., are they women, children, disabled, not disabled, wood building, straw building, and what we'll do is to multiply them all together. Hazard times exposure times vulnerability. And that was our risk. That's how we used to calculate risk. That's how most of the world still calculates risk. In fact, this is how almost all the world calculates risk. Still. But what I've told you now is that we've missed a very important part of this equation. We've missed out time. Because after the earthquake, your risk now has changed, because the world you live in now is completely different. So we cannot ignore time. And that's just to sort of, using words and balls. We have to turn this into mathematical equations and then start putting into computers to be able to understand how we can do this, understand this, and protect people better. And that's the limit of human knowledge right now. That's as far as I can take you, because we don't know what the next step is. And we're working on it. We have lots of bright people working on it. But that's literally as far as I can take you. This is the same picture I showed to the UN, the same picture I showed at the COP meetings, the same picture I showed at the United European Commission, because no one else knows how we can do the next step. And we need to do the next step. And we are working on it. Ask me again in 5 years' time. I might be able to show you a better slide. So this is my last slide. And I want to end this talk because it's been a very gloomy talk. Low death and disasters. But the context, I want to show you the broader context of this, because the broader context is actually a really good thing. Because this is the number of people who've died in disasters, of natural causes, in the since 1900, last 100 odd years. And in the early 20s, nearly 500,000 people were dying in a natural event, whether it's a hazard, earthquake, tsunami, hurricane, whatever. And that number has dropped precipitously over the last 80 odd years. And that's amazing. That's the context, right? We've done really well at saving people all over the world, mostly because we're very good at managing floods and famines and droughts and heat waves. But we can get that down to zero. Well, as close to zero as we possibly can. And so I work in this space here. How do we squeeze this even more? But the context is we've squeezed it a lot already. So that's the good news story. That's the good bit I want to end on. So to summarize some of the things I've talked about today. The earthquake in Turkey is just another one of those tragic reminders that, when you're not prepared for earthquakes, and when earthquakes multiply with social vulnerabilities, you get devastating impacts. And so this is the key thing. This is why natural hazards become disasters. It's when a hazard compounds and interacts with the social vulnerabilities of exposure, poverty, and corruption. That's when you get a disaster. But remembering that all these exposure vulnerabilities can be spatially different. Southeast Turkey is worse than Northeast Turkey, remember? Northwest Turkey. Spatially heterogeneous. But also these things evolve with time too. So that wheelchair person is much more exposed after the earthquake to the tsunami than they were before, for example. And so if you want to really understand disaster risk, you need to understand the physics of how earthquakes work and buildings shake. But you also need to understand the social and the built environments people live in. So this is my plea for geographers, as well as geologists to work together, and psychologists. And also you can't just think of disasters as one thing. An earthquake, that's it. The time component matters too. So if you really want to keep people safe, you have to understand that multi-hazards are really what you're trying to fix. You're not fixing an earthquake, you're not fixing the flood, you're fixing the flood and the earthquake and the flood cascade. The whole thing needs to be safe. And climate change is going to make everything worse. So we need to be understanding what the impact of climate change is going to be on what we do in our science. And we're working on this. So that's the positive news. We are working on this. We are aware of where our flaws are. And we're trying to fix it. That's it from me.
Right, well, it falls to me to give you the vote of thanks, Ekbal.
Thank you very much.
Firstly, can I thank you for a magnificent example of how earth science is really practically applied to social humanitarian need. I don't think we've ever had such a comprehensive examination of the consequences of geology and the consequences of people's interactions, varied though they may be, with geology. So could I thank you, could I ask audience here to thank you in the usual way for most entertaining, slightly dark, but very informative evening's presentation. Thank you so much.
Thank you all. Thanks very much.